Welcome back to my lecture on probability and statistics, and in this section we're going to talk about simultaneous events where we care about both outcomes being successful. So the first question we have is, what is the probability of drawing a red marble and flipping the coin heads? Well, we know that the coin flip does not impact the bag of marbles, and similarly, picking a marble doesn't impact the coin in any way. So we know that these are independent events, so we said that's the probability of red times the probability of getting heads. Now, this is pretty simple, but what happens if we want to know the probability of drawing a red marble and a green marble? Well, drawing the red marble impacts whether or not we'll draw the green marble. Why is that? Because there's less marbles in the bag. So we know the first event. Either we're going to draw the red marble first or we're going to draw the green marble first. It doesn't matter which one it is, and I'll do it both ways. So we'll assume we draw the green marble first. Well, if I drew the green marble, then the next probability will be the red marble, assuming or given I drew the green marble first. Similarly, I could draw the red marble first, and I could draw the green marble given I drew the red marble first. So the question now becomes, what is the probability of drawing the red marble or the green marble given I drew the other one? Well, we know that we can count. So the probability of green, actually, I already have it written down here. The probability of green is equal to 1/2. Now, if I have a green outside of here, so let's look at this sample space. If I drew green and it's out, I have red, red, green, green, yellow. I only have 5 marbles left. So now my probability has to be a red, which is 2 out of 5. I have 2 reds out of 5 marbles left, so that's 2 out of 5. So the probability of both is the probability of doing one of them first, then doing the other one given I did the first one. The other thing we can look at is here, we can flip these, and we'll see the probability of red, which is 2 out of 6, which is a third, times, now I have, let's do this in a different color, I have 1 red, 3 greens, and 1 yellow. And now I can see that my 3 greens are out of 5, so this will be a 3 out of 5. So you'll see here, this cancels and I get 1/5, and this cancels and I get 1/5. So these are actually equivalent. So the probability of me picking 2 marbles out of the bag and it being a red and a green marble is equal to the probability of me drawing a green marble first and then a red, or me drawing a red marble first and then a green. So another way we can look at this is I'm going to flip a coin twice, and we're going to see why this formula results in a different answer. So I'm going to ask the question, what is the probability of heads and heads again? Okay, so we know we're going to flip the coin once, so we'll pick any one of these events. We'll flip the coin and it's the probability of heads. All right, now I'm going to say the probability of heads again, given I flip the first coin heads. Well, we know the first probability is going to be equal to 1/2. But when we look at the second probability, after I flip the coin, my sample space does not change. It's still heads out of 2 possibilities with equal likelihood. So this is still 1/2 because this section right here, probability of heads given heads is equal to the probability of heads. So this, which is equal to 1/4, is unaffected by conditionality. So I actually could rewrite the probability of 2 independent events simultaneously as the product of the probabilities. However, I have to use Bayes' theorem to understand conditional probability. And we'll look at how this is a discrete probability distribution function in the next section.